Here is an alternative notation for limit. You can say limit as x approaching a of fx is equal to L. Another way of writing it is fx approaches L as x approaches a. Fx approaches L as x approaches a. They are both acceptable. All right? But you should be comfortable with both. Notice the phrase, but x not a, in the definition of the limit. Remember, in your definition of the limit, not equal a. So your a value, x is not equal to. All right? We never consider x equals a. In fact, fx need not even be defined when x equals a. The only thing that matters is how f is defined near a. So this limit business is spoken always near your number. Okay, let me explain with an example. Here is a picture. All right, maybe you can see the details. Here is a graph. Notice it is continuous. There is no broken point. Okay. Look at the second graph. It is not continuous. At A, fx is not here. There is a hole there. At A, fx is here. So height at A is here. Here is a third graph. This is fx, graph of fx. At A, there is a hole and there is no other value. So at A, it is not even defined. In the previous case, at A, fx is defined, but it is not there. That is, your graph is not continuous there. Whereas here, at A, fx is defined and makes the graph continuous. Notice the limit when my x values go to A from the left. My fx values are below. The fx values approach L. When I approach A from the right, my fx values come from the right. First, you're increasing, then you're decreasing, and you're approaching L. I don't care what happens at A. Look at the second example. At A, the value is this. But when x is approaching A, the value is approaching L. Whereas this is something far away from L. Likewise, when x is approaching A, the value of fx approaches L, height L. Okay? That's the difference between here and here. The value of A is also L. Here, the value of A is not L, it's somebody else, but the limit is L. In the last one, the value of A is not even defined. There is no value for A, but limit is defined and limit is L. This is limit from the left, this is limit from the right. Okay? So I hope you have some feel for this. Here is an example. Guess the value of the limit. Look, when x approaches 1, I get 1 minus 1 over 1 minus 1. So denominator is 0. So when x is 1, the function value is not defined. But we want to find the limit. Okay, limit is different from function value. Let's find out what happens when limit x approaches 1 of this fx. That is, you're looking at x's near A, but not equal A. So here is, when x is to left of 1, so less than 1, different values of x, look at different values of fx. Looks like I'm getting close to 0.5, right? We are starting at 0.66667, reduce. We are getting close to 0.5, not going below it. When x is bigger than 1, so x is greater than 1, my value of fx is 0.4, 0.47, 0.49. So I'm getting closer again to 0.5. So the basis of these two tables, we are guessing that the limit is 0.5. Limit exists, but the value at 1 does not exist. Limit at 1 exists, but value does not exist, okay? Look at the picture. So that is the graph of y equals x minus 1 over x squared minus 1. If you go close, you will notice the value does not exist at 1. But as you come towards 1, from the left or from the right it seems you are increasing towards height of 0.5. From the left it seems you are decreasing to the to the height of 0.5. All right, that was using our tables. So consider the function gx, which is x over x squared minus x minus 1 over x squared minus 1 for any x other than 1. But at x equals 1, you give it height 2. Okay, let's change f slightly. Then this looks like exactly this, but there is a small difference. Look at g. At 1, it gets height 2. Okay, so essentially the same graph, essentially, but not really, because at 1, you have a certain height. Okay, so g at 1 is 2, but limit of gx as x approaches 1 is 0.5. All right, so g has the same limit, but the value now is 2. All right, so we'll come to one-sided limits in our next videos. Okay, until then.